on, record. You said 9b. 9b says what is the, or how many electrons rather pass through the appliance every minute. So this is going to be related to current, Angelina. We know the current is 20 amps, which is 20 coulombs of charge per second. So we want to turn coulombs per second into electrons per minute. So the easiest way to do this is to turn this thing into, so I got 60 seconds per minute. That's going to cancel out my seconds. And I have 1 electron is 1.6 times 10 to the negative 19 coulombs. We're just converting units like we did before, right at the very first chapter we looked at unit conversions. That's what we're doing here. So my coulombs are going to cancel, my seconds are going to cancel, and I'm going to get a monstrous number here. Let's make sure we're actually right. 20 times 60 divided by 1.6 times 10 to the negative 19. I get 7.5 times 10 to the 21, which is what we're looking for. Electrons per minute. Cool? Okay, anybody else? Going once. Is that a question? Okay. Like for 10b you're talking there? Well, they said, yeah, the answer they gave is 20 plus or minus a half, so 20.2 would certainly fit in with that range.
Yeah, but was the answer like exactly 20?
It's the slope of a line of best fit.
Right.
So it's not going to be exactly anything, but the line of best fit should be around 20, and then we gave it with that half. I would probably be a little bit more generous. I would probably say anywhere between 19 and 21 would be an acceptable slope, plus or minus a full ohm. But yeah, you should be able to, if you're drawing a line of best fit the way I taught you to draw a line of best fit, assuming you've plotted your data properly, you should all get around 20 ohms, give or take an ohm. Anything else from those 10 questions? Going once, twice. Okay, I told you guys that you were going to need computers today. Get your computers out. Get your computers out. If we need to go raid either Shapansky's room or Easton's room,
We got a full-on raid.
it's our turn. Here's what I want you to do. Flip the page in your notes to this. It says Series and Parallel Circuits Simulation. You guys are going to have the opportunity to play with some circuits without worrying about breaking anything. Yeah, see, I know, but it's like you gotta be a little safe before we get a little reckless. So grab your computers, those of you. I'm going to show you all what we're going to do, and then we'll go get computers for those of you who need. So you are going to, it says there to open the FET, okay guys, it says there to open the FET Simulation Circuit Construction Kit. There are actually two. If you Google Circuit Construction Kit, you will, very slowly, because I have lots of tabs open, the first set is the Circuit Construction Kit DC, FET Interactive Simulations. This is the one that you want. The other one is the AC. You don't want the AC. AC is a lot more complicated. You're not going to be learning about AC circuits unless you do a full-on electrical engineering degree at some point in your future. So you're going to open up the DC construction kit. Yep, there is. It's true. We're going to get this guy going here. I want to turn this on and this one off. Nope. this one off. There we go. Whose? Yours? That's unfortunate. Nope, that's the wrong display. That's okay. I don't actually think it matters which one you choose. The only difference between the intro and the lab, you get more stuff to play with in the lab.
You want DC?
Yes, you want DC. Okay, and open the lab. Why not? Let's go to the lab. Full send. Let's do the real stuff. Play with some more stuff. And it'll give you something that looks like this. Are we all kind of here?
No. Yeah.
If you have a computer, we're still waiting for computers to load? Okay. On the side here, these are all of the items that you can use to build your circuit. We got wires, batteries, light bulbs, resistors, and switches.
And more.
Wires, always more wires. A fuse, a battery, light bulb, and a resistor. Why there are multiple bulbs, I don't know. Wire again, a dollar bill. Like, why is there so many duplicates? You know what? Forget it. Let's go back to the intro. We always get wire. I don't know why we always get wire.
No, let's go back to the lab.
Okay. Yeah, we also have a dog. If you want to throw a dog in your circuit, you're welcome to throw a dog into your circuit. The dog might die. Right here, you've got an option to either use the fun little, hey, look, there's a battery, or you can use the schematic notation that I gave you guys yesterday.
Which would you recommend?
I'll let you play. You can use whichever you choose. There is, later the questions will guide you through something that might help you decide which one to use. But you can build the whole thing without, you want to turn this. Ta-da, we have a light bulb. Okay. You can have the values listed here, so that's a 9-volt cell. If you double click on these things, you can change. Maybe you want to increase the voltage. We want a 120-volt battery, maybe. You can change the polarity of these things. You can see that changes the direction of the current, or we can just get rid of it entirely. Okay. Up here on the right where it says show current, you can either have the electrons flow or you can have conventional current. It's up to you how you choose to play with that. And then you've got your voltmeter here. You can move these pieces independently of each other. Or you've got your ammeter to measure the current. The current just measures it at a particular spot. So if I have, let's make a simple circuit. We're going to like that. We're going to go like that. And then we're going to go like.
When you use too much of the battery, it starts burning. My battery is on fire.
Yeah, see, there we go. You found the batteries are on fire. The ammeter, you just put the crosshairs over top of the wire wherever you want to test the current. The voltmeter, again, like we talked about yesterday, the voltmeter is going to measure it over top of things that use voltage. So if I use my voltmeter here, if in this particular wire, the voltage drop between these 2 points in the wire should be 0. There's nothing using voltage in there. But if I go over here to my resistor, the only load in my circuit, is using up all of the voltage provided by the battery. So that's how you would set up your voltmeter. Like I said, you could have the electrons or you could have the conventional current. We said electrons flow from negative around through to positive. The conventional current goes from positive around down through into the negative. Again, you can put whatever you want in here. All sorts of random stuff you could do. But I would ask that you, as you play, you work your way through the lab activity thing that I've got for you here. Okay. Yeah, do use the intro one. The lab one gives you access to some other things that I don't want you to get too confused with. Yeah, use the intro one. Did you kill the dog?
Yeah.
Seriously?
No, I didn't kill
Yeah.
him. They just didn't like it very much.
He barks at you?
I guess so. I didn't know my sound was up.
I never had that. What did you do?
I just put 120 volts through him.
You put 120 volts. Let's see what the dog does.
That's how all this.
Okay, we're gonna electrocute the dog. Okay, and we want the and do turn the values on. Okay, so the resistance in the dog is 100,000 ohms. Let's crank up the voltage on the dog. Dog doesn't like that. I like it. What if we put a dollar bill in there? While you're playing, if you could also do the activity, that'd be great. Interesting. Okay, here you go. If you need a computer, we're gonna send you guys upstairs to. I'll just call Shapansky's room. Shapansky. Mr. Shapansky, this is Mr. DeWeedoff. You got the computers up there? Myers has them. Interesting. Okay, thank you. Bye. Okay, how many computers do we need? 2? Okay. Myers has 3? Yes.
Not good. You know what that means, Andy? Very simple what happened. Cinco más? Yes. Sei beaucoup. Whoa. Wait, does a dollar translate? You know, unfair. Putting your hand in the wall. This is way more than enough. That is simple. Listen, this is 100,000 ohm. Coming from 100,000. Wait a minute.
Okay. Ken, Joe, you're gonna have to keep sharing with Manuel.
Oh, you found the big
Oh, we
batteries.
should look a little bit.
Disconnect the batteries. So it's already taken a row. You wanted 3, right? Like 3 individual cells. Oh, yeah, 1 and 2 together. What, how many percent?
Oh, you know what?
There you go. There you go.
What did you guys find? Eric. Sorry? They don't add. They, in fact, the total voltage is what? What was the total voltage in, so if I had 3 9-volt batteries attached in parallel, what did you guys find the voltage to be? Sorry? In parallel. We did this, right? Did we actually do it? Question said, attach 3 identical cells in parallel. So let's attach 3 identical cells in parallel. 1, 2, 3. I'll attach them in parallel. Yes, you are is profound. It made a letter E. So what's the total voltage does what? Not only do they not add, the total voltage is what? Yeah, equal to the voltage of each individual cell. So why might we want to do this?
Increase battery life.
To increase battery life, yes. Cool. I had you guys draw, or it said to I asked you guys to draw or construct and then draw a simple circuit. Did we have any issues with this? Okay. If we have no issues with this, I wanted you to do a few things. I wanted you to note the brightness of the bulb, observe the electrons as they move through the circuit. In the simulation, the light bulb has a default resistance of 10. Wires have a resistance basically of 0. Do the electrons move at different speeds throughout? Explain why or why not. Gurkir and I kind of talked about this in front of the class. What did you guys find? Do the electrons move at different speeds when moving through different areas of the circuit? No. Are we cool with why that is? This is the part that Gurkir and I were kind of talking about in front of the class. Why? This is the fundamental piece, right? So why are the electrons even moving?
Because there's a circuit that's forcing them to move.
The circuit's not forcing them to move. The circuit's just providing them a place to go. Nowhere along the wire is there anything forcing the electrons ahead.
Okay.
What is the current's just flowing charge? What causes the current to happen?
Oh, I think they are like the other electrons are negative, so they can like stack together.
Correct.
So they push each other to the direction that they go into.
Right. So the circuit just provides the electrons that are repelling each other a place to go. So as the electrons flow, if they encounter a place of high resistance, it's going to slow. What are we doing, Manuel?
I'm filling the water bottle.
With the computer.
He's
Okay.
on
In a circuit, you got the electrons that are repelling each other. When they hit an area of high resistance, they slow down there. So what does that do to all of the electrons that come behind? Slows them down. Because they're being repelled by what's coming ahead that's been forced to slow down. What happens to the electrons once they get out of the area of high resistance? Why are they slowing down? Well, what's causing them to move forward? No. The repulsion of what's coming behind. So even though these electrons now exist in an area of low resistance, if there's nothing coming from behind pushing these guys on, are they going to move quickly? No. So you get an area in the area of resistance in a circuit slows the entire thing down because it's repelling what's coming behind and it's not pushing forward the electrons that are moving ahead. So that's why it doesn't matter where the electrons are in the circuit. They don't have their own little motor like a car does, driving around traffic. Their speed is dictated by what's pushing them from behind and what's ahead of them. Does that kind of make sense? Okay, so that's the why there. Current versus voltage. What is the relationship between these two? Yes, Connor.
As your voltage increases, amps go up as well.
Okay.
Increases as well.
Volts go up. Means current goes up. I love it. How about current and resistance? What did you guys find there?
The higher the resistance, the more less current.
Current goes down, or sorry, as resistance goes down, current goes up. Or as resistance goes up, current goes down. So they have what's called an inverse relationship with each other. Okay, and then we moved on. I had you guys build a slightly more involved circuit. This one was a series circuit involving one 9-volt cell, a switch, and 3 light bulbs in series. I asked you to draw a schematic diagram for that. You want something that looks something like this. There's 1, 2, 3. There's my diagram, something that looks like that. The light bulbs all had a default resistance. They were all the same. What did you find as you measured the voltage in each one of the light bulbs? This one, light bulb 1, light bulb 2, light bulb 3. This is 9 volts.
The voltage is the same in all the light bulbs and the current too.
Yeah, so assuming that you left the resistances all the same, you would have found that this voltage, the total voltage provided by the battery was 9 volts. What were these values? They were all the same and they were all 3.
It's like the circuit that we did with the 3 batteries, like the same as the 1 batteries. I don't know exactly.
How about the current? What did you find the current to be everywhere?
I changed my resistance.
Okay, we'll get to yours in a second. Sorry? 0.3? Everywhere? Even in the battery? Connor, you use different values for the resistance in the light bulbs. What were your values for voltages?
Oh no, I got 0.3.
No,
Sorry.
values for the voltages.
No,
But you said you changed the resistance.
something else is looking the wrong thing.
No, you're looking at the wrong thing. That doesn't help us. Did anyone change the voltage on? Yeah, Tanjo. 1.914. 1.9 volts. Your second one was 1.15, and your third one 5.14. What was your 9.4? 1.9, 1.15, and 5.94. What was the voltage you had in the battery? What do these three numbers add up to? So what does, by changing the resistance, we actually see a little bit more of what's going on here. How do voltages behave, or voltage drops is what these things are. They're objects that are using up voltage. How do they behave in series? Yeah. The voltage drop across each of their objects combine to give us the total voltage provided by the battery. So the way we write this is we say, well, my voltage total provided by the battery is going to equal V1 plus V2 plus V3. We have those drops. What do we know with the current? It's the same everywhere. So the way we write that is we say that the current total is equal to the current through 1, which is equal to the current through my second lamp, which is equal to my current through the third lamp. Current's the same everywhere. And the resistance is an interesting one, because to actually define the resistance, you'd have had to go do some calculating. How do resistances behave in series? If you were operating on the default, this one would have been 10 ohms, this one would have been 10 ohms, and this one would have been 10 ohms. To figure out what my total resistance is in the circuit, I would have had to go and I say, okay, well, I have 9 volts provided here. I know my current is 0.3 amps. What's R? Well, we know that resistance is equal to V equals I times R, so R equals V over I. My voltage was 9. My current is 0.3. What's 9 divided by 0.3? And I'm wondering if that should be actually 0.3 repeating, but we'll find out. So how do resistances behave in series? If I've got 3 light bulbs connected one after the other, how does their individual resistances relate to the total resistance provided by the circuit? Someone just say the sentence. How do these 3 relate to this one? Yeah. In series, the resistance total is equal to the resistance or resistances of all of my individual objects added together. This is what I was hoping you guys would just kind of stumble upon as you went through this activity. Parallel circuit did what? What did we find? Some stuff. Yeah, that's not helpful. So we've got my circuit with my 3 light bulbs connected in parallel. There's my schematic diagram. What were the voltages, and this is a 9-volt battery, what were the voltages in each light bulb? Sorry? Everything was 9. That's interesting. And how about the current? 0.9, 0.9, 0.9, and 2.7. Yes, sir.
Mine was really weird. One of mine was 9 and the other two were 4.5.
Did you change the resistances?
No.
Then you did something weird. What that means is you didn't have 3 light bulbs in parallel. You had 1 in parallel and 2 in series.
Okay.
Yes. That tells me you didn't build it properly. So, what is the voltage rule then for things connected in parallel? The voltage provided by the battery, the total voltage is going to be equal to what? The voltage down each one of these branches, right? My total voltage is going to be equal to my voltage drop across each of those branches. How about my current?
The current, so current 1 plus current 2 plus current 3 is equal.
Sweet. And the awful one is resistance. If I wanted to find the total resistance of my circuit, I would take my, just like before, R is equal to V over I. If I want total resistance, that's going to equal my total voltage divided by my total current. So my total voltage was 9. My total current was 2.7. What's my resistance? My total resistance for the circuit. 3.3 repeating. And we started with 10 ohm resistances in each one of those bulbs. So how do we get from 3 10 ohm resistors to a total resistance of 3.3? And does this even make sense? How do I add a bunch of 10 ohm resistors to a circuit and lower my overall resistance?
Divided, 10 divided by 3 and take out this number.
Okay. Why does that work? The way, if these all look the same, then it looks like I just take my resistance and divide it by the number of objects that I have. But what if my resistance, these resistances are all different?
I think that you add together all the resistance, then divide it by the number, like, that's it? No. No.
Adding the resistances together wouldn't give me what you're looking for there.
Yeah.
I'll give you that relationship here in a second. This one gets really. Did anyone build this with different resistances in these resistors? Tanjo, you did? What were your resistors?
10, 22, and 7.
So you had 10, a 22, and a 7. Your voltages were all still 9?
Yeah.
What were your currents?
0.9, 0.41,
Sorry, 0.9,
9,
0.41,
1.29,
1.29, and your total was?
2.59,
This is current. Sorry, say that number again.
2.59.
2.59. So we still see that my currents are adding together. Let's redo this calculation with Tanjot's numbers. The total resistance, RT, is going to equal my total voltage, which was still 9, right?
Yeah.
Okay. Divided by 2.59. What's our total resistance?
3.47.
How is this related to this? It can't be a clear addition because 0.9 plus 0.41 plus 1.29 isn't going to give me, 10 plus 22 plus 7 isn't going to give me 3.47. So how do we get from these values to this? Luis's suggestion of saying, well, I just take my total and divide by how many, or take my individual and divide by how many there are, would have worked here, but is not going to work here. So then what's the relationship? I'll give that to you momentarily. Flip the page. Comments, questions, concerns on any of this? other than the total resistance here at the bottom, which we're going to do in a second? This is kind of how I was hoping you guys would go through it. So let's do this. Kirchhoff's laws and series and parallel circuits. So between what we did now and what you were supposed to do in grade 9, we've already kind of seen that we can connect devices to circuits in two ways. We can connect them in series or in parallel. And there are no other ways. The manner in which we attach the components of the circuit can affect the nature of the circuit, in particular, its resistance. And there are a number of laws that govern all of this that we must use, and we call these things Kirchhoff's laws. The Russian physicists put these things together for us. You've seen this one already. For a series circuit, there is only one path for the current to flow, so the current must be the same everywhere. So if I have a circuit that looks like this, I'm going to draw a simple circuit here on the side. I've got a circuit, and instead of a bunch of light bulbs, I'm just going to draw resistors because they're easier. I've got resistor 1, resistor 2, resistor 3. My total current is the sum of all of my, in series, the current is equal everywhere. It doesn't matter what object it's going through, the current's going to be the same throughout. In a parallel circuit, you get something that looks like this. That's resistor 1, resistor 2, resistor 3. We found already, doing the activity you guys just completed, that my current here, I total, is going to equal what? IT has to equal the sum of all of the currents in the branches, which kind of makes sense, right? Every time you have one of these junctions, a place where the wires split, the current is going to split as well. You're going to have some that's going to follow this path and some that's going to follow this path. Likewise, when you get to here, some's going to go this way, some of it is going to go this way. So in parallel, for current, the total current is equal to the current through all of the different individual branches. So in a series circuit, the current must be the same. And in a parallel circuit, the currents flowing through each pathway add. So Kirchhoff's current law says that the sum of currents entering a junction must equal the sum of the currents leaving a junction. What goes in here must be the same thing that comes out here. What goes in here is the same thing that has to come out here. They got to add. So that's the current law. The voltage law we saw too. Kirchhoff's voltage law stated the sum of the potential differences in a circuit must add to 0. And the reason for this is just a way of restating the law of conservation of energy. Where you've got the energy provided by the cells has to equal the energy used by the loads. And the load could be a resistor, the load could be a light bulb, load could be anything. It's important to remember that there's an increase in potential across the terminals of a cell, and that there is a decrease in potential across a load. Just a restatement of what I've just written. The increases in the drops have to add to 0. In a series circuit, it's relatively straightforward. I'll redraw a series circuit for us. Little guy down here. So I've got something that looks like this. There's 1, there's 2, there's 3. My voltage drops have to equal my total voltage supplied has to equal my voltage drop in 1 plus my voltage drop in 2 plus my voltage drop in 3. Or my total minus V1 minus V2 minus V3 equals 0. You can think of it that way too. So we've got the current law, we've got the voltage law for series. Flip the page when you're ready. We'll do the voltage law for parallel. I should have put that blank page somewhere else. I don't know why I don't know why that's snuck in here. For a parallel circuit, we've seen it already. A parallel circuit looks like this. No, I want to keep going. One sec. It's in the video, and yeah, take a look at it later. So we've got my voltage in 1, my voltage in 2, my voltage in 3. And this is my total voltage. We've already seen that the voltage across every one of these branches used up has to be the same as my voltage supplied by the batteries. So in this case, over my parallel one, I've got my total voltage is going to be equal to my voltage drop across the first branch, which is going to be equal to my voltage drop across the second branch, which is going to be equal to my voltage drop across my third branch. Because you can view these things as being independent of each other. So you've got, like, this is one small circuit. This is another circuit. This is another circuit. So each one of these three has to use up what's provided by the battery at the beginning. Where things are going to get a little bit weird is when we've got resistors in a bunch of different places, but we'll play with the circuits here in a bit. Note, the potential difference is the same. Across parallel branches. Now, the last one, Kirchhoff didn't have a law for resistance. But physicists have combined Kirchhoff's laws with Ohm's law, and there are some really gross derivations. I'm not going to make you do the gross derivations. I'm just going to tell you what the results are, and we can reason our way through them. For a series circuit, as we added resistances, what did that do to the total resistance of my circuit? As we added resistances, our total did what? What did you guys find out? It increased. Thank you very much. And specifically, it increased by what we added to it, right? RT was equal to R1 plus R2 plus R3 plus dot dot dot. What have you know, as we keep adding resistors in series, they're going to continue to add. The total resistance in a series circuit is the sum of the resistances. Since each electron must push its way through each resistor, it should make sense that the resistances are cumulative. Parallel is where things got weird. As we added resistors in parallel, RT did what? Sorry? It dropped or decreased. Which is what this sentence says right here. As we add resistors in parallel, total resistance decreased. Why? What happened? And what is the relationship? For the sake of not spending all that time going through this nasty derivation, I'm just going to tell you what it is. The relationship looks like this. It's 1 over the total resistance is equal to 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistor. So I could rewrite this and make it look like this. RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, which we were never going to come up with looking at tangent values. Luis's values gave us, it brought us a fair bit of the way. Because if we looked here, I mean, maybe we can do this in our head. If I had 1 over 10 plus 1 over 10 plus 1 over 10, that's going to be 3 over 10. And then 1 divided by 3 over 10. When I divide by a fraction, I multiply by the reciprocal. So instead of having 1 over 3 over 10, it's going to be 10 over 3, which is exactly what Luis said it should be. I take what each equal resistor is, and I divide it by the number of resistors. That works in that very specific case where all the resistors are exactly the same. Tangent provided us with an example where all the resistors were different, and we were never going to come up with this relationship. But here it is. If the electrons are forced through one path, then there will be much more friction than if there were multiple paths to choose from. So by providing multiple paths, you're lowering the total overall resistance. We're going to finish this up tomorrow, and we'll play with these circuits in more detail. I've got some examples. I've got a lot of problems for you to do. It's going to be great. And that's how we're going to spend tomorrow's class. When the bell goes, you may also go. If you did not finish playing with the circuit constructor kit, that's your homework. There we go.